Precipitation and agglutination assays. So to start, we're going to talk about antigen-antibody binding. Affinity is the initial attraction force between a Fab site on an antibody, or the part of the antibody that binds to the antigen, and an epitope or determinant site on an antigen. So something that you have to think about is that it's not just like puzzle pieces fitting together. All of these things are made up of proteins, and proteins are made up of amino acids. And from biochemistry, you should have learned that all amino acids have side chains, and those side chains have different charges to them and different structures, which makes them positive or negative, hydrophobic, hydrophilic, and those types of interactions are going to cause the protein to fold in a particular way. Now, the very specific antigen that the antibody is supposed to bind to has also proteins, has also those amino acids, and has those folding structures, so that when it comes together, it's not just the physical folding into the correct shape to get them to stick together. It's those intermolecular forces that are happening, those opposite charges attracting, or the hydrophobic molecules coming together, or the hydrophilic molecules come together, hydrogen bonds, those types of interactions between the molecules that are actually going to be holding them together. So that all has to do with affinity. So affinity is that initial attraction force between the antibody and the antigen. Or in other words, the part of the antibody that binds to the antigen and the part of the antibody that binds to the antigen that binds to the antibody. So those two molecules coming together. The strength of attraction depends on the specificity of the antibody for a particular antigen. If the antibody is super specific and it finally finds its antigen, that antigen is going to bind pretty tough, or in a pretty strong way. If the attraction, or if the antibody isn't as specific, it's not going to bind as strongly. So the more the cross-reacting antigen resembles the original antigen, the stronger the bond will be between the antigen and the binding site. So here is a picture of some antibody binding site, and then you can see the opposite charges and how they're lining up here and how opposites attract. So this one wedges in here, all happy. This one wedges in here because the negatives are going to enjoy having the presence of the positive here, and the positives are going to enjoy having the negative charge here. But here you can see this part is happy, but this part down here not so much, because negative charges are going to repel each other, so this is going to have a lower affinity. Now when we talk about cross-reacting antigen, we're talking about antigens in the body that weren't supposed to be recognized by that antibody. And that's where some of our autoimmune diseases can come into play, or allergic reactions, some of our hypersensitivities, where instead of the antibody binding to what it was supposed to bind to, it binds to something else that's kind of similar to that antigen. And then it starts a chain of reactions that can be detrimental in the body. So that's what we're talking about with the cross-reacting antigen. Avidity is the sum of the attractive forces between an antigen and an antibody that keeps the molecule together. So it's not just affinity, like that initial attractive force, it's the sum of the forces that keeps the molecules together. It involves the strength with which a multivalent antibody binds a multivalent antigen. And it's a measure of the overall stability of an antigen-antibody complex. The law of mass action. K is equal to the concentration of the antigen-antibody complex divided by the concentration of the antibody times the concentration of the antigen. Free reactants are in equilibrium with bound reactants. The value of K depends on the strength of binding between the antibody and antigen. So if we have more of this and less of the independent ones, then we're going to have a higher K. If we have less of this and more of the independent ones, we're going to have a lower K. So the higher value of K, the larger the amount of antigen-antibody complex molecules exist, the more visible or easily detectable the reaction. Precipitation reactions involve combining soluble antigen with soluble antibody to produce insoluble complexes that are visible. It requires the antigen-antibody to have multiple binding sites for one another and equal relative concentration of each. The zone of equivalence. So this precipitation curve that you can see here has the prozone, the zone of equivalence, and the postzone. And this is so important because sometimes you can't just add antigen to antibodies and expect to see a reaction. Or you can't just add antibodies to antigen and expect to see a reaction. It takes a known concentration of each before you can determine that there's a reaction. So even if a person had a particular antibody in the serum, or if they had a particular antigen in the sample, we don't know if the concentration is unknown and we don't add the correct amount of antibody or antigen to it, we may never detect it. So it could go undetected just based on concentration issues. So the number of multivalent sites of the antigen and antibody are approximately equal. To be detectable, precipitation reactions must be run in the zone of equivalence. So we have to have the antigen concentration and antibody concentration just right before we start to see those antigen-antibody complexes form in this lattice-like structure. So if we have too much antigen, it's going to saturate all the binding sites and you won't see these big complexes form. Because you can see this is shared between here and here. And this one is shared between here and here, and this one is shared between here and here. So that is the exact amount of antigen and antibody needed to form these massive complexes. If we start to have too much antigen, each one of these binding sites is actually going to be blocked with antigen. So you're not going to see any of that lattice formation happening. And it's not going to be detectable with the naked eye. In the prozone, you don't have enough antigen. So if you don't have enough antigen, then you definitely can't form those complexes. So the prozone phenomenon, antibody excess. Antigen combines with only one or two antibody molecules. There's no cross-linkages that are formed. The cross-linkages are forming this lattice-like structure, and that can be visible with the naked eye. False negative reactions may occur as a result of high antibody concentration. If a false negative reaction is suspected, diluting out the antibody and performing the test again may produce a positive result. Post-zone phenomenon, antigen excess. Small aggregates are surrounded by excess antigen. No lattice network is formed. The presence of a small amount of antibody may be obscured, causing false negative results. The test is repeated about a week later with a specimen to give time for further production of antibody. If the test is negative again, it is unlikely that the patient has the antibody. There's a bunch of different types of precipitation reactions, and this table is a good reference table for you to review. There's a few of those that we're going to go into more detail with. So radial immunodiffusion. In radial immunodiffusion, or RID, it's a single diffusion technique. Antibody is in the support gel, and antigen is applied in a well that's cut into the gel. The antigen diffuses out until the point of equivalence is reached, the endpoint method. The square of the diameter is proportional to the antigen concentration. So we have standards, standard 1, standard 2, standard 3, and then an unknown. So we graph these standards and we mark the distance away that the antigen has diffused into the agar. So the agar has antibody in it. We're going to have a well cut into the agar, and then we're going to insert our antigen. Now the antigen is going to migrate out, and as it migrates out, it's going to reach a point to where it forms the antigen-antibody complexes. And when it forms those, they're going to be so large and form that lattice that they're not going to migrate any further. So they kind of stop at that point. And at that point, you can calculate the concentration of the antigen. And the way that you calculate that is, like I said, there are standards that you would graph. And then when you graph out the standards, you can say, okay, now let's compare the radius of the unknown and put it here. And so the diameter of the precipitation ring. And then we would mark that here on the line that we formed. And then now we can get the relative concentration of what we were measuring. Immunofixation electrophoresis. So immunofixation electrophoresis is a double diffusion technique. Unknown antigen is electrophoresed, and then an antibody is applied directly to the gel. Precipitates form where the antigen-antibody combination has taken place in the gel. This technique is used with serum as the antigen to determine over and underproduction of antibody types. So here is where we have the gel, and it will migrate through the well, and then we treat this with particular antibodies, and then we can stain those to determine where the bands are to see where different things that we're measuring are going to come up and what the relative concentration is based on the density of the bands. Agglutination is the visible aggregation of particles resulting from combination with specific antibody. It's a two-step process. First is sensitization, initial binding. Antigen and antibody unite through antigenic determinant sites. And then you have lattice formation, the formation of large aggregates. Rearrangement of antigen and antibody bonds to form a stable lattice. It's produced by antibodies called agglutinins. So here's our antibody. Here's our antigen with multiple determinants. You have the sensitization, which happens, where you're not going to see a visible reaction. And then you're going to have this lattice formation, where you have visible agglutination. Types of agglutination reactions. There's direct agglutination, uses known bacterial antigens to test for the presence of unknown antibodies in the patient. The Widal test, a rapid screening test used to determine the possibility of typhoid fever. It uses Salmonella O, somatic, and H, flagellar antigens. So another direct agglutination, hemagglutination, involves red blood cells and the ABO blood group typing. So we have a red cell button after centrifugation, and we're going to shake it. 4+, one solid clump. 3+, several large clumps. 2+, numerous smaller clumps. 1+, barely discernible clumps. And then negative smooth suspension. So the antigen and antibody are mixed and rotated. If there's strong agglutination, you're going to see large clumps in a clear background. Weak agglutination, you're going to see small clumps in a cloudy background. And negative, even suspension and cloudy background. So you can do it in a tube, or you can do it on a slide. Passive agglutination employs particles that are coated with antigens not normally found on their surfaces. Erythrocytes, latex, gelatin, silicates, synthetic beads or particles provide consistency, uniformity, and stability. Passive agglutination is used to detect rheumatoid factor, antibodies to group A strep antigens, antibodies to viruses such as rotavirus, cytomegalovirus, rubella, and varicella zoster, and antibodies to hepatitis viruses and HIV. The process, antigen is attached to the carrier particle. Agglutination occurs if patient antibody is present. Reverse passive agglutination used to detect microbial antibodies. Common applications would be rapid identification of antigens from infectious agents. For example, group B strep, Staph aureus, streptococcal groups A and B, rotavirus, and Cryptococcus neoformans. Detecting soluble antigens in urine, spinal fluid, and serum. An antibody is attached to the carrier particle, and agglutination occurs if the antigen is present in the patient sample. So here's a comparison of the two. So starting out with passive. In passive, you have these carrier particles that are mixed with soluble antigen. That forms coated particles. Then you're going to add those coated particles to the patient sample. And if the patient sample has the antibodies in it, you're going to see agglutination happen. Patient sample having antibodies means that they've been exposed to one of these infections. Down here, you have carrier particles that are mixed with antibody. So now you have these like capture antibodies. And with these particles, you're going to put them into the patient sample. Now, if the patient has the antigen, then those antibodies that you added that are specific and known to react with a certain type of microorganism, that's going to bind to those antigen. And that's going to cause agglutination to happen. Agglutination inhibition is based on competition between particulate and soluble antigens for limited antibody combining sites. Lack of agglutination is the positive reaction in these types of tests. They're used to detect antibodies to certain viruses such as rubella, mumps, measles, influenza, parainfluenza, HBV, herpes virus, respiratory syncytial virus, and adenovirus. So, in your patient sample, if they have the antigen, what's going to happen is you're going to add reagent antibodies. So these are known antibodies against the antigen that we're detecting. So if they have the antigen, it's now going to combine with the antibody. If they don't have the antigen is going to be free and not have anything attached to it. So immune complexes form up here, but they don't form down here. Then you're going to add antigen-coated particles. So these guys are already pretty much blocked. So when you add those particles, you're not going to see any clumping, and that means that this person actually did have the antigen. With these guys down here, these antibodies were free because there was no antigen in the patient sample. The patient didn't have the antigen. These antibodies didn't have anything to bind to. So when you add antigen coding particles, now they can form their lattice, and this is a negative test. This means that you're going to see agglutination, but that's because the person didn't have those antibodies, which would have been blocking in this scenario. Something kind of similar here. So you've got, you're testing for antibody now. So if the antibody is present in the patient sample, you're going to add known antigen. When you add known antigen, this antigen is going to combine with the patient's antibodies to form these immune complexes. The immune complexes are then, you're going to add red blood cells, and the red blood cells are going to do nothing with those immune complexes because the immune complexes have already been formed. If the patient does not have the antibody, what's going to happen is that when you add the antigen, there's not going to be any binding of that antigen. So when you add the red blood cells to it, the red blood cells are going to be like, hey, nothing else is bound to this antigen, let's bind. And they're going to bind, and that's going to indicate that the patient didn't have the antibodies against it in the beginning. So here's a comparison table where you can take some notes on the different types of agglutination reactions, their principal and expected results. Instrumentation, particle counting immunoassay uses nephelometry, involves a laser and an optical particle counter to measure the number of residual non-agglutinating particles in a specimen. It measures serum proteins, therapeutic drugs, tumor markers, and certain viral antigens. Quality control and quality assurance, you want to avoid cross-reactivity by using a monoclonal antibody direct against an antigenic determinant unique to a particular antigen. So that's a lot of terms there. So monoclonal antibody means that it is a very specific antibody that is designed to recognize a very specific antigen. Store reagents properly and check expiration dates. Account for sensitivity and specificity of the specific test kits used and be aware that a negative result does not rule out the presence of the disease or antigen. And then you can review the summary.